This video is going to do two things. So I want to go over the retailing problem or mini case in detail with you. And I'd also like to be able to showcase R Markdown. So right now I have an R session going, and we would normally have a program in the upper left. We have our console in the bottom left, where we get to see the commands that get executed as well as the output from those commands. And then off to the right we have our plots. Now the way we create a new program would be just go make a new R script. Instead of that, you can go down to creating a new R Markdown document. So I'd encourage you to get familiar with this, because it's one of the best tools for documenting an analysis. So often I end up doing an analysis and then I go do other things for a week or two, and then I have to come back to the analysis, and by that time I've often forgotten what I did. Markdown is an environment where you can have your code, the output from the code, and your comments all in the same document, and you can produce either an HTML or a PDF that will be very, very good for documenting and even sharing with your audience. So instead of creating a new one, let me show you the retail RMD that I've created. All right, so you have a couple different types of things. So you have I can set tags that are going to show up. I can insert R code. So anything that's in these quotes is a chunk of R code. Now, if I'm just developing a program, maybe I want to run that chunk of code. So I can click here and it runs it. And the output is shown immediately below that chunk. And then we could go on to the next chunk of R and run that separately as well. Another thing that you can do is put HTML code within this. You can just type if you want. You can give yourself a heading. So for example, you can say # reading in the data. And that will create a heading. Or you can use HTML as if you know HTML. This is an unordered list, and so we're going to get a bullet list with these comments that I've left for myself. All right, now once you've created your whole document, you simply knit it. So I'm going to go hit knit, and if you look below, you can see it's 25% of the way through, and in a matter of seconds, we're going to get an HTML file that has everything that we just did. So remember, I typed a heading with the # reading in the data. Well, that shows up in large bold font. We have a list of all the commands that were executed. And then we get to see, okay, R actually loaded those libraries. It read in the data. And then here's the output from that names command that I executed. Here's my HTML code. So remember, I had what's called an unordered list. And so we have a bullet list with everything in there. I had used the B tag. So let me just show you what the B tag looks like. This means boldface. And so that turns on boldface in HTML. And that's exactly what we're seeing. All right. Let's now talk about the case itself. So this case addresses one of the major problems all retailers face, which is, which of my customers should I promote? So you don't want to promote customers that are going to just throw your promotions out and not respond. And so you'd like to be able to have a forecasting tool to predict how likely it is that a customer will respond to your promotion. So the way we usually do this is we look at a previous promotion that happened. So this retailer sent out a promotion, and in my data set there is a variable called target amount, And this target amount is the amount that the customer spent in response to this focal promotion that we're studying here. So this is going to be the dependent variable. Very often in data mining and machine learning, we use the term target to refer to the dependent variable. So target amount means this is the dependent variable, and it's the amount that the customer spent on this promotion. Now, all the other variables are known at the time that the retailer has to decide whether or not to promote a customer. So they can be used to inform which customers to send the promotion to and which ones to rest. So for the purpose of this analysis, I'm only going to focus on 3. So these are famously known as RFM, so recency, frequency, and monetary value. Recency is just the amount of times and the number of months since the most recent purchase by this customer. Frequency is tot ord, and that's the number of previous orders that a customer has made. And then monetary is tot sale, which is the total amount spent in the past on orders. How much has this customer spent in the past? Well, let's go fit our first model. So my first model is, you can see my R code here, is I'm just going to regress the amount spent on the promotion on RFM. And then I'm going to produce a diagnostic plot. So this week we're really focusing on diagnostics. So let's look at our plots. Now, here's a residual plot. The residual plot is probably the most useful diagnostic plot that you're going to have available. And the residual plot plots the residuals. So that's y minus y hat. How much is your prediction off from the observed value as a function of the predicted value. So these are y hats down here. And the ideal residual plot, remember I told you, should not show any patterns. And I like to joke that it looks like a snowstorm. So snowstorms don't have any patterns. It would just be a bunch of random dots. This is far from being random dots. This red line is a smoother. It's showing the middle of the scatter plot. And the red line is just tracing this row of dots down here. So how could that possibly be? The way that could be is that there's a ton of dots down here. So to understand why that is, let's go look at a histogram of target amount. And what you're going to see is a giant bar that includes 0. So I ran a little table down here showing that 95% of the customers don't respond to the promotion. Okay, so the amount that they spend is all exactly 0. Only 5% have positive values. So this red line is 95% of your data. And so all you're doing is you're taking whatever predicted value. So 0 minus the predicted value gives you this line. And so there's obviously a pattern here. It's not random, not a snowstorm. This data set is very challenging. Well, the way to handle this situation is to fit what I call a two-step model. This is a reasonable way of handling. It's not the only way, but we will fit some sort of a classification model to separate out the buyers from the non-buyers. So let's just first figure out whether or not you're going to place an order. And then among the buyers, let's figure out how much you're going to spend. So once I have that amount model built, I can apply that to all my customers. We're going to see how that works when we get through the classification chapter. So for now, let's just focus on the buyers. And so give me 2 seconds here. I'm going to shut off email. Otherwise, we're going to keep getting emails. All right. So I'm going to use some dplyr code. We're going to do more dplyr in a couple weeks. But this command right here says I want to make a brand new data frame called buyers. And that data frame is going to be my data frame that I read in. We're going to send that to a filter where I only keep cases where the target amount is greater than 0, meaning they bought. There's also a few cases where the total sale in the past is negative. That's probably due to returns. There's not many cases. I'm going to omit those as well. And so you see we go from about having 50,000 cases down to about 3,000 cases. Well, let's go fit another model now with only my buyers. So now my N just went from 50,000 down to about 3,000. And let's go look at our diagnostic plots. Well, our residual plot, I can't say it's gotten that much better, to be honest. There's clearly a pattern. This red line really ought to be hugging zero. So the residuals on the average should be zero. That's an assumption of the model. They're clearly not. So there are problems with my fit, and this model is not very good. The next plot, diagnostic plot that R provides you is the QQ plot. This plot evaluates whether the residuals are normally distributed. And if they are, the QQ plot will produce points that fall on a line. Well, these clearly don't fall on a line. Now, as I mentioned in one of my other videos, normality is not a big deal because the only time we really need normality is significance testing, and we're not really doing significance testing here. But it's not a horrible thing to have normally distributed residuals, and we sure don't have that right now. So there's another problem. The next plot I like to call a more sensitive version of a residual plot. We're going to plot the square root of the absolute value of the residuals. So this would be like we're removing the signs, if you will, and we're going to plot that against the fitted values. This is not looking good. We have issues. There's a hint of heteroscedasticity in that the spread is not as great here. Then it gets pretty large. We're not doing a good job with this data set. The last diagnostic plot that R provides you with is called the leverage plot. So I'm going to make a separate video on standardized residuals and leverage, but what you want to look for here are points that have a Cook's distance that's certainly greater than 1 as a problem, greater than 0.5 as a problem. We have some points that are close to this 0.5 contour, indicating that this point has a lot of leverage and influence on our regression. And so this is not looking good either. So the upshot from looking at these diagnostic plots is we have problems with this data set. Well, why do we have problems? All of our predictors are highly right skewed. So let's just focus on frequency for a moment. What this histogram is saying is most of your customers have not bought from you very often. You get a very rare customer who's bought from you 120 times. So think about how many retailers, this is not a grocery retailer, but clothing retailer that you've bought from 120 times. That's a very rare customer. So this is a very skewed distribution. Now I want to remind you that regression and OLS make no assumptions about the distribution of the x's. So in one sense, it's not a problem that this x is highly skewed because it's not really assumed by the model. But highly skewed x variables will create, while it doesn't violate an assumption, it creates some problems for us. So let me describe what those problems are. Monetary is equally very skewed. So to understand the problem, I've used ggplot here with smoother superimposed with confidence bands. So these are 95% confidence bands for the mean prediction. Think of it as a confidence interval for the line. And so what you should notice is that these confidence bands get very wide. Our estimated line is very unstable off to the right. There's another way to generate this plot, which is using the GAM function. And I kind of like that version a little bit better because we get a rug. So these lines down here resemble a shag carpet. Each one of these lines shows a data point. So we have one value that's like 120 something previous purchases. We have another value that's like 90 some previous purchases. And then the vast majority of customers are down here. So our estimate of the line is extremely reliable down here because we have so much data. It's extremely unreliable off to the right because we have so few data points. And these data points out here exert a lot of leverage on the line, and they destabilize our estimate. So while a right skew distribution is not assumed, or we're not forbidden by OLS estimation, it creates a problem for us in that we have unstable estimates. So that's we're going to have to deal with that. So I generated some other plots. I'm not going to discuss those right now. Well, I'm going to go make myself a new variable, which is something that we often do when we're building data mining models. In fact, this is one of the keys to building a good data model, is creating the right variables in the first place. And so that's a topic that we're going to come back to in a couple weeks when we do feature engineering. But when you work in an industry for a while, you start to get experience on the variables that you should be creating. So in retailing, the average order amount is usually a very important variable. So that's just how much have you spent divided by how many orders. So if I spent $500 in the past, I'm a very different customer if that $500 was spread out over 10 orders, which means I tend to buy very small orders. That'd be an average order size of $50, versus if I had $500 over 2 orders, means I like to place big orders. So that's what AOA captures. Now, if I make a histogram of the logarithm of this, we get something that looks pretty normal. And when we fit a regression model with a predictor variable like this, we're not going to have the same issues with an unstable regression line. Well, let's go fit an extremely simple model. I'm going to use the log of my dependent variable. Now, I should mention the rationale for taking the log of my dependent variable is that we have heteroscedasticity. So the variance of my earlier scatter plots increased with the mean. So whenever you have heteroscedasticity, the remedy for that, one remedy, is to take the logarithm of your dependent variable. I'm also going to log the predictor variable, and the rationale for that is I want to capture diminishing returns. I want to allow for that. So this is a multiplicative model, very important model. I tend to use this model a lot. So often my variables are amounts or counts. The log-log model is really ideal for that. Well, let's go look at our diagnostic plots. My residual plot is looking very good. I don't see any real systematic patterns. The red line is close to hugging the 0 line, so that's a good thing. My QQ plot is looking much more like a line. There's a little bit of an issue here. One of these tails is a little bit heavy, but other than that, the QQ plot is much improved. Here's my other residual plot. It's looking pretty good. That looks like a snowstorm to me. And my Cook's distance plot, you're going to see the Cook's distance contours don't even show up, meaning that all my Cook's distance values are very small. So there's nothing problematic at all. I don't have any high leverage observations in this data set anymore. So once you've taken logs, the problems with high leverage often go away. All right. The only other thing that I want to discuss with you is the interpretation of the multiplicative model. So there's a whole lecture that you should be watching in my course packet on the multiplicative model. But as a review, we can take this estimated regression equation and state it. So here's our estimated regression equation. To avoid writing out target amount and average order, we're going to put in X is average order amount, Y is the target amount. So what is the interpretation of our slope and intercept here? Well, bit different than with simple linear regression. I'm going to exponentiate both sides. If I take the exponent of the log of y, I end up with just y. If I take the exponent of the right-hand side, I end up with e to the 2.65 power. And then that plus sign in an exponent becomes a multiplication. So times whatever my average order amount, x, is, raised to the 0.41 power. And so think of 0.41 as being kind of like the square root. If the power were 0.5, this would be exactly the square root. But this is going to be something like the square root function. I'll just note, if my slope were 1, then y would be proportional to x. It would be y is equal to some constant times x to the 1, and you'd get a line. Well, let's just go see what this looks like. We expect it to look something like a square root function, and sure enough, that's exactly what it looks like. So the function starts at 0, 0. So if x is 0, then y is also 0. We're constraining it to go through the origin. But then the function goes up with something that looks like a square root. So you get a very large increase between x equal to 0 to 100, much smaller decreases for every step of 100 thereafter. So we get diminishing returns. That's what the model is telling us that we need. One last thing, I think I fitted, actually I guess I didn't fit. I fitted the residuals, a similar plot to the one that I showed you earlier. I'll leave this as an exercise since I think I commented it out. The line that you have that's equivalent to this with the log-log model has pretty constant error bars around it. So we have avoided that problem by taking the log-log model. All right, so in summary, it's a very common task to want to be able to forecast the future amount that a customer will spend on a promotion. How do you deal with it? Number one, split buyers from non-buyers with a classification model. We'll talk about that when we get to the classification chapter. In order to predict the amount among buyers, use this multiplicative log-log model, and that will solve a lot of your problems. Number three, the interpretation of these coefficients is a slope of 1 means y is proportional to x. A slope less than 1 means that you have diminishing returns. A slope greater than 1 means you have increasing returns. So go watch my video on the multiplicative model. Also watch what I call the business failure example. It's a problem that illustrates a lot of these interpretation issues with the multiplicative model. So that's another really good video to watch. All right, that's it for this video.